Every successful lyophilization cycle begins with a step that is often underestimated: freezing. Although it may appear to be a simple cooling process, freezing determines the internal structure of the product and directly influences drying efficiency, product quality, and the success of the entire lyophilization cycle. At the beginning of the cycle, the product exists as a homogeneous liquid solution containing water, active pharmaceutical ingredients, and excipients. As the shelves begin cooling, heat is gradually removed from the product, causing its temperature to decrease uniformly. Contrary to a common misconception, ice does not necessarily form the moment the solution reaches its equilibrium freezing point. Under carefully controlled conditions, the solution can continue cooling below this temperature while remaining in the liquid state. This phenomenon is known as supercooling and plays an important role in determining the subsequent freezing behavior. Eventually, a stable ice nucleus forms within the solution. This event, known as nucleation, marks the beginning of solidification. Once nucleation occurs, ice crystals begin growing rapidly throughout the product, while latent heat released during freezing causes a temporary increase in product temperature. Following nucleation, ice crystals continue to grow as additional water molecules join the crystal lattice. At the same time, dissolved solutes, including buffers, sugars, and the active pharmaceutical ingredient, are progressively excluded from the growing ice crystals, resulting in an increasingly concentrated unfrozen phase. By the end of freezing, the product has developed a complex internal structure consisting of interconnected ice crystals surrounded by concentrated solutes. This frozen architecture serves as the template for the porous structure that will remain after sublimation during primary drying. The size of the ice crystals formed during freezing has a significant influence on the drying process. Larger ice crystals produce larger pores after sublimation, reducing resistance to water vapor flow and generally allowing faster primary drying. Smaller ice crystals, in contrast, create finer pore networks that increase mass transfer resistance and can extend drying time. Several process variables influence freezing behavior, including cooling rate, formulation composition, container geometry, fill volume, and nucleation conditions. Optimizing these variables is essential for achieving consistent product quality and robust manufacturing performance. Although freezing occupies only the first stage of the lyophilization cycle, it establishes the product structure upon which all subsequent drying depends. Many challenges encountered during primary drying can often be traced back to decisions made during freezing. In this episode, we explored how freezing transforms a liquid formulation into a structured frozen matrix. In the next episode, we'll examine ice nucleation and ice crystal growth in greater detail and discover how microscopic events during freezing can determine the efficiency and quality of the entire lyophilization process.